Right. So, in our course selected topics in decision modeling, we are in our 23rd lecture, and this will be on multivariable unconstrained non-linear programming. Now, last lecture, if you recall, we had studied the single variable unconstrained nonlinear programming. But there most of the situations they are not going to be single variable. There could be multiple number of variables, that it may not be a single variable, there could be number of variables that may be present, and they could be interacting, and that can be represented in the objective function, and the constraints would also be similar for multiple resources. There are different numerical methods that exist for solving multivariable nonlinear objective functions or constraints. So, let us see what are they. Now, although conceptually they are similar, but there are multiple variables they are present. So, earlier if you recall, we had taken the first order derivative and equated it to 0 to really indicate a slope change, and therefore, the position of an extrema, and thereafter taken the second derivative as a sufficient condition to find out whether it is a maxima or minima. But when you have multiple variables, instead of first and second order derivative, we really have to take the gradient, that is the del operator, and the Hessian matrix, which will be an equivalent of the second order derivative. So, essentially we need the two things, the first of all the gradient, and second of all the Hessian matrix, and again the equivalent of putting the gradient equal to 0 and the Hessian matrix, whether it is negative or positive, should be established also. So, those are the challenges that will be there for the multivariable unconstrained problems. Now, let us see how exactly they are. So, here are some examples, that is a single variable problem, f x equal to 12 x minus 3 x to the power 4 minus 2 x to the power 6. And the other one, if you can see that x 1 square plus x 1 into 1 minus x 2 plus x 2 square minus x 2 x 3 plus x 3 square plus x 3, that is a multivariable problem. So, as they are all unconstrained problem, we have not taken any constraints. So, basically what we need to find out the maxima for these two problems, that example you can see, and in other situations you can have minima as well, right. So, if they are the multivariable unconstrained problem, now we have come to the next stage, that is how do we solve this multivariate unconstrained problem. So, essentially the problem is that we have to minimize or maximize f x, where x varies from x 1, x 2, x 3 to x n, and the problem is to be solved for each x values that satisfies the constraints, and we have to have the minimize the function. So, there are two conditions, one is called the necessary condition in terms of the first order derivatives, but in this case partial derivatives, is it all right. So, that is our del operator. If f x reaches the extreme point, whether maxima or minima at x equal to x star, then the first order partial derivative of f x is also found at x star. That means, we must be able to have the first order partial derivative defined at that point, is it all right. So, it should not be that the function is not continuous, and therefore, we do not have the partial derivative existing at that point. So, that is the first condition, that the partial derivative should actually exist. After that, once we know that yes, at that particular point we have the partial derivative existing, then we put individual partial derivatives equal to 0, right. So, the solution of these the individual equations that you shall find by putting the partial derivatives equal to 0 will be our the value of the extrema. But we have to also have what is known as the sufficient condition. The sufficient condition that should be in terms of the second order partial derivatives, and these matrix that the second order partial derivatives will form is called a Hessian matrix, right. The Hessian matrix has to be either positive definite or negative definite, or there could be situations where they are neither positive definite nor negative definite. Now, how to know whether a Hessian matrix is positive definite or negative definite? We shall see in due course of time, but just know this, that if you know that the Hessian matrix is minimum, then positive definite, then we are going to have a minimum. But is it a global minima or a local minima, that is also to be ascertained. Now, exactly what are we saying here is that when it comes to the global minima, the global minima has to be suppose there is a curve which is actually having multiple peaks. For multiple peaks we shall have what is known as a and if you reach a particular one, that could be called as a local minima or maxima. So, Hessian matrix can indicate yes, it is a minima or maxima, but it does not really tell that whether it is an global one, right. So, that require further knowledge about the concavity or convexity of the graph, which has to be established separately, right. So, let us look at the gradient. Now, the gradient at a specific point x equal to x star is nothing but a vector whose elements are the respective partial derivatives found at x equal to x star, right. So, that we call it, let us say, the del operator del f x star equal to del f del x 1, del f del x 2, del f del x 3 and up to del f del x n at x equal to x star. Is it all right? So, that is the concept of gradient. So, it is all the partial derivative with respect to all the variables that we have at a given point. So, that is the definition of gradient. So, here is an example. Supposing we have a function f x equal to 15 x 1 plus 4 x 2 cube minus 3 x 1 and x 3 to the power whole square. So, what should be the value of the gradient? Now, we need to find out the first order partial derivative with respect to x 1, x 2 and x 3. So, when we take the first order the partial derivative of the function with respect to x 1, tell me which are the terms which will be useful for us, right. So, as you know, in case of partial derivative, the first term which is 15 x 1, this term is going to be used. The second term, that is 4 x 2 to the power 3, this will not be taken simply because there is no x 1 term in that. The third one, that is 3 x 1 x 3 whole square, there is an x 1 term. So, when you differentiate, the first 15 x 1 will give 15, second term will return 0 and the third term will return 3 x 3 square, right. So, that will be our del f del x 1. So, similarly, del f del x 2 will be only the second term is having x 2. So, 12 x 2 whole square, and third term will be obtained from the third term again, because first two terms do not have x 3 and that would be minus 6 x 1 x 3. So, now what do? We combine them in the form of a matrix that you can see that matrix here. So, this is our matrix. So, this is 15 minus 3 x 3 12 x 2 whole square minus 6 x 1 x 3. So, this entire thing will be our del f x, that is the gradient. Is it all right? So, we have the gradient, and for this particular function that is obtained. So, another example, this example is slightly little more complex, because we have an e term, that is f x is e to the power x 1 and within bracket 4 x 1 whole square plus 2 x 2 whole square plus 4 x 1 x 2 plus 2 x 2 plus 1. Now, this has to be, if you differentiate it with respect to the x 1, then this differentiation has to be done in parts, right. In the first one we differentiate e to the power x 1, and e to the power x 1 differentiation is e to the power x 1 itself. So, you can see this term, that is e to the power x 1, and the whole of the second term will come, and in the next stage we keep e to the power x 1 as it is, and we differentiate the term. So, we take the x 1 thing. So, we have 8 x 1, and there is one more that is here. So, we get 4 x 2, right. So, it will be e to the power x 1 8 x 1 plus 4 x 2. But with respect to x 2 it will be easier, because e to the power x 1 will be not coming into the picture here. There is no need to do that differentiation. So, if you simply multiply them, then actually we have the first term is not a function of x 1, second term is a function. So, it come to 4 x 2, then third term gives 4 x 1, next term gives 2. So, e to the power x 1 4 x 2 plus 4 x 1 plus 2. So, that will be our del f del x 2, and when you combine them all, all these terms. So, this one is the first term, that is this entire term is here, and this is the second term that is here. When you put them together, that will be our gradient. Is it all right? So, this is how we actually calculate what is known as the gradient. So, first of all we have calculated for two examples. In the first example we had 3 variables. So, we took the partial derivative with respect to each of the 3 variables, and when you put them in the form of a matrix, that will our gradient. And in the second example is a 2 variable problem. We separately again found partial derivative with respect to x 1 and x 2, and when you combine them, that time we got the gradient. So, you know how to really find out the gradient. We have to put gradient equal to 0 to find out our extreme point. Now, the significance is this: the change in x that maximizes the rate at which f x changes is proportional to the gradient. The rate at which f x increases is maximized if changes in x are in the same direction with the gradient, right. So, as long as the direction is same, then you keep going, but at a point when the slope changes. So, gradient really represents the slope. So, at some point the slope really changes, and when the slope changes, then the directions will be different also. So, accordingly the problem should attempt to move in the same direction of the gradient as much as possible until it reaches at optimal point, because what happens at optimal point? The optimal point the slope changes, right. We have seen in those convex or concave functions that the slope keep increasing in one case and then it decreases, and in the other case the slope decreases in case of minima and then it increases after the extreme point. Right. So, the objective of an unconstrained multivariable problem, that is maximizing, is to find the feasible solution x star while maximizing f x, and the problem should attempt to move in the same direction of the gradient as much as possible until it reaches the optimal solution. So, that is how we make use of gradient to solve problems. Now, having seen the gradient part, let us see the other one, that is the second order partial derivative matrix or the Hessian matrix. The Hessian matrix is a square matrix of second order partial derivatives of scalar valued functions and developed by German mathematician Ludwig Otto Hesse, right, and is again used to know the direction at any point of the curve for which we need maxima or minima. So, what is Hessian matrix? So, you look on this side of the screen, we have a Hessian matrix format. So, supposing a function f which is really having a number of variables, let us say x 1, x 2, x 3, x 4, x 5, x 6 and all the way up to x n, then Hessian matrix will be del square f del x 1 square, then del square f del x 1 del x 2. Basically, it is nothing but del x of the del f del x 2, right. So, del x 1. So, all of these terms are basically taking del x 1 of del f del x 1, del f del x 2, del f del x 3 and up to del f del x n, and then the second term is with regard to del x 2, and obviously the second term there will be then del square f del x 2 square, and finally at the end del square f del x n del x 1, del square f del x n del x 2, del square f del x n del x 3 and finally del square f del x n whole square. So, these entire matrix can be called as the Hessian matrix. Now, look how to really find out Hessian matrix. So, let us take an example, that is f x equal to x 1 square plus x 2 square. So, first we need to find out the gradient. What will be the gradient? What is the partial derivative of this function with regard to x 1 del x 1 of the function? Only first term, is it not? So, we take the first term and we find the derivative and we get what is known as 2 x 1. And if we do it with respect to x 2, that is del f del x 2, then we get 2 x 2, because only the second term will come. So, the gradient will be del f del x 1 del f del x 2, that is 2 x 1 and 2 x 2, right. So, now what will be our Hessian matrix? The Hessian matrix we have to find out first of all del square f del x 1 square. Tell me what it is. If you take del x 1 of del f del x 1, now the del f del x 1 is 2 x 1. If you take it again del x 1, what will be the value? You have guessed it correctly, it will be 2, right. And what will be del x 2 of del f del x 2, because again the value is 2 x 2. So, it will be 2 again. So, those two terms we know. Now, we need to find out what is del x 1 of del f del x 2 and what is del x 2 of del f del x 1. Look here, del f del x 1 is a function of x 1 because it is 2 x 1. So, if you take del x 2, it will be 0. Similarly, del f del x 2 comes out to be a function of x 2 only, that is 2 x 2. So, if you take again the partial derivative with respect to x 1, that is del x 1, that will be 0 again. So, what will be the Hessian matrix? I hope you have understood now what will be the Hessian matrix. So, let us see what it is. So, we have the function x 1 square plus x 2 square and we have taken the gradient, and the gradient has come out to be 2x1 and 2x2. Now, we compute all these 4 terms. The first term, as you have seen, that del square f del x1 square is 2, because this value is 2x1. So, it becomes 2. The last term del square f del x2 whole square is the del x2 of this. So, it will be 2, but the other terms are 0, as you have seen just now. So, if you put them all in the form of a matrix, that is our Hessian matrix, and that Hessian matrix will be 2 0 and 0 2, right. So, I hope you understood how to really obtain the Hessian matrix. I know that is the first part of the thing. So, let us take one more example. So, these example we have also seen earlier, that is the other example, that where f x is 15 x 1 plus 4 x 2 cube minus 3 x 1 x 3 whole square. So, when you have taken del f del x 1, del f del x 2 and del f del x 3, we really got the gradient. Now, what will be our Hessian matrix? So, when you take the Hessian matrix, the first term is a differentiation of this with respect to x 1. So, what will be that first term? It will be definitely 0. What will be the second term? The second term will be second term is required del f del x 2. So, del f del x 2 is 12 x 2 whole square. So, if you differentiate is by del x 1, what will you get? 0 again. And what will be the third term? This is your del f del x 3. So, if you differentiate it with respect to del x 1, what will you get? You will get minus 6 x 3, is it not? So, like that you can get the Hessian matrix. So, this is how the Hessian matrix is obtained. Let us see each term. Supposing this term, just now I said that del f del x 3 is minus 6 x 1 x 3. So, if you differentiate with regard to del x 1, you get minus 6 x 3. So, again let us see how this 24 x 2 is coming. So, this is our this is our term, that is del f del x 2. Again if you differentiate, that is del x 2 of the term, then we will get 24 x 2. Similarly, third term minus 6 x 1 x 3 is del f del x 3. Again you differentiate it with respect to, that is del x 3, it will get minus 6 x 1, right. So, rest of the terms are 0. Let us see only this term. So, this term is del x 3 of del f del x 1. Del f del x 1 is this. So, if you take del x 3, the first term will get nothing, the second term will get minus 6 x 3. Right. So, I hope you have now understood how to obtain the Hessian matrix. The Hessian matrix is a matrix of second order partial derivative in a particular form, and the Hessian matrix has got a very important significance. And what is that significance in terms of nonlinear programming problem, right. So, we must understand that. So, in order to understand that, let us see what is the meaning of positive and negative definiteness of a Hessian matrix, right. So, a matrix we can find out their eigenvalues, right. So, you all have studied the concept of eigenvalues. I will show you how to find eigenvalues very quickly. It is not very difficult, rather easy. So, once you find out the eigenvalues, then you check that whether those eigenvalues are positive or negative. But the question is, see, the eigenvalues should be all positive or all negative or all greater than equal to 0 or all negative, that is all less than equal to 0. So, only these 4 cases are considered here. Can there be some other cases as well? Is it a complete set? Answer is no, it is not a complete set. Supposing we have 3 eigenvalues, 2 could be positive, 1 can be negative, right, or 1 is positive, rest 2 are negative. So, if we have combination of the eigenvalues both positive and negative, then we cannot really conclude whether the Hessian matrix is either positive definite, negative definite, or positive or negative semi definite, right. So, only in these 4 cases are defined, rest of the cases we are not going to take up, in the sense that in that case it will be difficult to conclude, right. So, now if the all the eigenvalues are positive, then we call it the Hessian matrix as positive definite. If all the eigenvalues are negative, then we call all the Hessian matrix as negative definite. And if all the eigenvalues are greater than equal to 0, that means positive, but greater than equal to 0, then we call the Hessian matrix as positive semi definite. And finally, if all are less than equal to 0, then we call the Hessian matrix as negative semi definite. Now, let us see how to find out the eigenvalues. Now, you see we got in our example one of the situations where Hessian matrix is 2 0 0 2, that was our Hessian matrix. So, we know that we have to have a characteristic equation. The characteristic equation for obtaining eigenvalue is given by the absolute value of H minus lambda I equal to 0, where H is the Hessian matrix and I is the identity matrix. So, what we do? 2 0 0 2 minus lambda 0 0 lambda, that is what you get by multiplying an unity matrix 1 0 0 1 with lambda matrix, right. So, that is lambda 0 0 lambda. So, we put that equal to 0. So, if you put that equal to 0, then what are we going to get? See, we get a matrix 2 minus lambda 0 0 and 2 minus lambda, is it not? That is the matrix that is now put equal to 0. So, that is exactly what is written here, that this will become 2 minus lambda 0 0 2 minus lambda equal to 0. So, when you try to solve them, then you multiply 2 minus lambda into 2 minus lambda minus 0 into 0. So, that is exactly what is written here, and that gives us 2 minus lambda into 2 minus lambda equal to 0. So, it is factorized already. So, we do not have to do anything. Therefore, we find lambda 1 equal to 2 and lambda 2 equal to 2 also. So, all the eigenvalues are found to be greater than equal to 0, that is positive. So, we then say the Hessian matrix is then positive definite. So, what does it mean? It really means that since the Hessian matrix is positive definite, that function, if you put equal to 0, that is the gradient of the corresponding matrix, we then get the minima, because we have a positive definite Hessian matrix, right. That is the significance. Let us take another example. Suppose the Hessian matrix is 0 1 and minus 2 and minus 3. So, follow the same procedure, H minus lambda I absolute equal to 0, then we get 0 minus lambda 1 minus 2 minus 3 minus lambda. So, you get this kind of format, and when you put them into an equation, we get lambda square plus 3 lambda plus 2 equal to 0. By simple factorization, we see lambda plus 2 lambda plus 1 equal to 0, or lambda 1 equal to minus 2 and lambda 2 equal to minus 1. So, all the eigenvalues are found to be negative, and therefore, the Hessian matrix is negative definite. Is all right. So, this is how we find the gradient, we find the Hessian matrix, and we find the eigenvalues of the Hessian matrix, and from there try to conclude whether the Hessian matrix is positive definite or negative definite, right. The positive definite Hessian matrix is connected to a minima when you put the gradient equal to 0, and negative definite Hessian matrix is connected to maxima if you put the gradient equal to 0, right. So, in our next lecture we shall see some problems related to this, right. So, thank you very much.